we are going to check out the molar volume of an ideal gas. And in order to do that and get down to this magical number of 22.4 liters, we just want to review quick Avogadro'S Law, that volume of a gas and the number of moles of gas are going to be a direct relationship as long as temperature and pressure remain constant. Then, if you take Avogadro's law and the combined gas law, Boyle's, Charles's, and Guy-Lassaic's law, and wrap those all together, you were probably taught the ideal gas law. PV is equal to nRT. Pressure times volume is equal to the number of moles of gas, a gas constant, and temperature. If I go ahead and I rearrange the equation, now moles is equal to pressure times volume divided by the gas constant times temperature. Both of these are just for a gas, one single gas. Now, if I have a mole of a gas at standard temperature and pressure, what's the gas volume? That's where this magic number of 22.4 liters comes into play. At standard temperature, 273 Kelvin, standard pressure 1 atm, you plug that in to this equation, and you're going to find in 1 mole, of course, and your gas constant, that volume is 22.4 liters. Now, 1 mole of a gas, that could be any gas. It could be hydrogen, it could be helium, it could be carbon dioxide, etc., is going to occupy that exact same volume as long as you have standard temperature and pressure. As long as you're at STP, we got that 22.4 liters. Now, let's say you're not at 1 mole at STP, you're at 2 moles. Then it would be double 22.4 liters. Let's say you're dealing with half a mole or 0.5. Well, 0.5 times 22.4 is going to be 11.2 liters. Direct relationship. One goes up, the other goes up. One goes down, the other goes down. In fact, remember what moles represent. Besides volume here, it represents the number of particles, atoms, or molecules for a gas. And that's where here we have the statement of Avogadro's law. 2 or more gases that are going to have the same number of particles if they have the same temperature, pressure, and volume. Again, if you think of the ideal gas law, PV is equal to nRT, everything being the same and you're calculating moles, it didn't matter what gas it is. Do remember, though, that not only is moles equal, or 1 mole equal to 6.02 times 10 to the 23rd of anything, that 1 mole of a gas at STP is 22.4 liters, but that 1 mole of any substance is going to have the mass in grams of whatever the molar mass is. If you're taking the New York State Chemistry Regents exam, there's a typical question that shows up with regards to molar volume, which I'm going to show you right now. Here it is, the classic New York State Chemistry Regents question. You're at STP, you got a 12-liter sample of, in this case, methane, and it's going to have the same number of molecules as, and here are your choices. Everything is at STP, and that means then it doesn't matter what the gas is, all that matters is it's then the same volume, which is choice 2. Typical question shows up a lot. One more thing. You see this equation here at the bottom. If you are dealing with gas stoichiometry, in other words, the mole problems as they relate to balanced equations, this doesn't show up on the Chem Regents, but if you're taking a high school chem course or an honors chem, then this might be something you're responsible for. The coefficients here in my balanced equation go for, of course, the number of molecules, it could be the number of moles, and now I have this relationship I can use it for when it comes to the volume of a gas at STP. So let's take a look. In this balanced equation then, as long as I'm at STP, I can calculate the volume of ammonia. I'm going to put X liters here, starting with 89.6 liters of nitrogen and excess hydrogen. Well, excess hydrogen means I'm not going to run out, right? And my 89.6 here means I can just use the mole ratio in order to solve this question. 89.6 liters over 1 mole is going to be equal to X over 2 moles. The mole ratio in the balanced equation, as long as I am at STP, works here. And all I'm going to do is I'm going to double the volume and end up with an answer of 179.2 liters for ammonia. Very simple are volume problems as long as we're at STP. As always, keep working hard and good luck.